This is the program that I created for a test lift that I also created to show you guys how the potentiometers work on a standard lift. So it's just a small test bed, nothing serious. And it just has a lift on it, it doesn't move around or anything. And I created this whole program just for it. So this is the main page of the program. And as you can see, it's not that much programming, but we have the user function here. This is where the large bulk of the programming is at, and the OC lift pot, which stands for Operator Control Lift Potentiometer. And we'll look at all of that programming in a minute. But first, let's look at what we have on the main page, because that's what's important. So if we go to Globals, we see PID requested value R and L. And they are set to float. Float is just more accurate. It goes down to a decimal point. Integer is to the nearest whole number, so it rounds it off. So float is more accurate, integer is slightly less accurate. It doesn't really matter which one you use, I just use float, but you can also use integer. So right here we'll hit OK. Now as you can see, these two are used right here, and these get analog input HRs. High resolution's the one I prefer. And what it's saying is that variable is equal to the current position of the potentiometer. So the potentiometer is where it is now. So let's say that value is 1,000, and the requested value is set to 1,000. The requested value is where we want to go. So the the lift, is trying to get there to that requested value. So that means that if the requested value is set equal to the current value, then that means it's not going to want to move. So if I push down on it, it will not move. And that's useful so you don't have to hold down the button all the time, because the way we programmed it is you hold down the button and it will go up to that position. But using this, you don't have to hold down the button once it gets to its maximum height. You can just let go of it and it will hold any weight that's put on it as long as it's not too heavy, which it shouldn't be. So that's useful just for keeping the position, since you don't have to hold the button the whole time. Just a convenience thing. If you don't want that, you can take it out. But it is used for something later. So next we have while loop, and that just keeps the values up to date, constantly changing as the lift moves. And then we have our user function. So let's go ahead and check that out. So let me scroll up. Alright, so first thing, let's check out all the variables we have, because there are a lot. We have all these types. We have float, float, float. Once again, doesn't matter. The integers can be floats, the floats can be integers. No difference really, just accuracy, and it's not even a big difference in accuracy. So those are all of ours. So let's look at the first two that are used. PID current value for both sides. L stands for left, R stands for right. So it says PID current value R equals get analog input HR. So what it's saying is the current value is equal to the current value. So the current position of the potentiometer. Simple as that. Now as you can see, the value is left blank, but some of these down here have values. Well, the reason this is left blank is because it is being calculated within the program. So any of these values that are left blank, that means that the program will give it its set value. There is no reason for you to put in a value, because it may mess with how the performance of the lift goes. So if it is being calculated inside the program, then just leave it at what it currently is, which is blank. So right here we have proportional code. What is proportional? Where did that come from? Another name for this type of program is PID, which as you can see we've seen at the beginning of most of our variables. PID, PID, PID. PID stands for proportional integral derivative, and it's usually known as PID control. And proportional integral derivative is the different sections of programming and how they're calculated. So right here we have the proportional code, so that's the P of it. So now we have PID error R, so that is being calculated from the program, so it is going to have no value, equals PID requested value R, which we saw in globals a minute ago, minus PID current value R. So if the current value R is, let's say we're at 1000, and the PID requested value R is 2000. So we want to get to 2000, we're currently at 1000. So you do 2000 minus 1000, and that's 1000, and that's your error, 1000. I know it seems like a large number, but they get multiplied by even smaller numbers, like decimal point numbers, that make it much, much smaller, and we'll see that in a bit. And then we have some limits here. So these limits, PID error R is less than 5, and PID error R is greater than -5. So if it is in between 5 and -5, then set it equal to 0. So if it is very, very close to the set position, which is when the error would be in this range, then it might as well be at the position because it's so very close. So you don't want your motors running and eventually overheating just to try to get to that position. So you set the PID error R equal to 0, and that will set the motor speed equal to 0 in the end equation. So that's just a limit. So if it gets very close, shut down the motors. Next we have integral. This is where the math gets a little bit more complicated, and you can't just do it in your head. Integral R is plus equals PID error R. So what does that plus equal mean? Well, it takes all the previous values of PID error R and adds them together. And that's your integral. It adds all the previous ones together. And that can be a very, very large number. But we have the limits here. So right here we have integral limit R and integral limit L down here. Well, what are those? So if we go back to our variables to reference, they are 500. Now you could also just put in 500 here. So instead of having it integral limit R just set equal to 500 in your variables, you could just replace this whole thing with 500. It would still work the same. But these are just limits to keep it from escalating to these super, super high numbers where the calculations would become very, very high. Even though they're being multiplied by these small decimal points, it would still get far, far too high. So it fixes that by setting these limits. And you may think, well, what about -500? What if it goes down into the negatives? Which is possible. There can be negative errors. Then we put the negative right there in front of our variable. Or once again, you could just type -500. And it will set a limit for -500. And see, then it sets it equal to -500. So if it goes above 500, set it equal to 500. If it goes below -500, set it equal to -500. So that's just to keep the numbers from escalating to a very, very high amount. Now, derivative code, the last piece. Derivative R equals PID error R minus last error R. Well, what is last error? Last error equals 0 in our program up in the variables. But here we have last error R equals PID error R. It's a little bit complex, but I'll try to explain it the best I can. When a while loop goes, it's very quick, but it still has to do things in order. It can do it in a matter of a millisecond, really, or, well, not necessarily a millisecond. It can do it very quickly is what I'm trying to say. Very, very, very quickly. But it still has to go in order of all of these things. So, if we say last error R is equal to PID error R. So, what is PID error R? PID error R is up here as well. So wouldn't this always equal 0? No. With the order of things, it calculates this and then does this. So last error equal to PID error. So it's setting it equal to the previous one to use when it comes back through the loop. Now it's a little complicated and a little confusing, so I'll just say it in layman terms. This uses previous errors to create a future prediction of where the motor speed needs to go for the lift. That's all it does. Now, the final equations for motor speed. This is where the motor speed is finally calculated from all that different program. Now we have PID error times Kp plus Ki times integral r, not integral, I always mispronounce it, plus Kd times derivative r plus Kbias. I know it seems like a lot, and you may wonder, what is Kp, what is Ki, what is Kd, what is Kbias? Those are constants. If we go back up to our program, they're all down here at the bottom. So the Kd is used for derivative, because d derivative, Ki integral, and then Kp is used for the proportional. So you match all those together. But then what is Kbias? Kbias is a constant that you add on, and it can increase or decrease everything. I prefer not to use it though, because it can drastically change how the program works, for the better or for the worse. But I didn't see a need to use it. So it's set to 0, so it's just adding 0, so it does nothing. Now, these values right here, we have 0.05. That is 1/20th. It's a very small number. So small that it doesn't have very much effect on the numbers down there, which is why they're all added together. But they're very large numbers, like the integral, the numbers could get up to 500, and the derivative can get high too, and so can the error. I mean, it got up to 1,000 in the example I gave earlier. So multiplying them by these smaller numbers, which these will always, almost always, be very small numbers below 1, sometimes even below 0.5, which this one is obviously below 0.5. But what I'm saying is that you'll have to adjust these to your own robot. On my little test lift, my test lift didn't have any weight on it, so these smaller values can help it lift up that small amount of weight that it's lifting. But on an actual robot, these values would have to be higher because of the amount of weight that's being put on them when you're moving around and carrying stuff. You would have to adjust these to your own robot's design. So that means you would have to do some trial and error and mess around with the values until you get what you want. And they will not always be the same like this. They will be different. So you'll have to test around with doing different ones. I can tell you now though that the proportional is usually the highest. So the Kp constant is usually the highest constant out of the 3 that I'm using right here. Almost always. So just make sure that you do not use these values, because they probably won't work. They're very small. Make sure you use larger values made for your robot. So now if we scroll back down, now we know what these are all set equal to. So these two, the integral and the derivative, are harder to calculate in your head. The PID error is rather easy, and the Kbias is just a constant. But in the end, after adding all those together, that's your PID drive. That is the value for your motor speed. And it will slow down and speed up as it approaches the value, and so on. So now we have our motor speed limits. The standard motor speed limit is 127 negative 127 in both directions, you know. Counterclockwise, clockwise. But what if the PID drive becomes over 127? It becomes very, very high. Well, you don't want that to happen. You want to set it to something that it can actually handle. So right here I have some motor speed limits. If PID drive R is greater than 100, set it equal to 100. So the motor speed will be 100. Now, I said the limit was 127, but you do not want your lift to go that fast. That is the maximum motor speed. If it goes too fast up, your robot can flip backwards. If it goes too fast down, your robot can flip forwards. You definitely do not want it to flip during competition. So, once again, these are something you might have to change. On my test lift, 100 worked fine for me, but on your lift, you may want it to go even slower. Because, what if you have more weight on it than my little test lift had? Then you're definitely going to want to lower this some, that way it doesn't flip forward when you try to go down, or flip backwards when you try to go up. Once again, so these are all adjustable. And I suggest setting them equal to each other, so 100, 100, 100, they're all the same. And see, it's the same for the negative here. Now we're finally getting into how are we going to know what the requested value is. I haven't said that the requested value is specifically equal to anything, except at the very beginning when the requested value was equal to the current position of the potentiometer, which will be used in a minute. So first we have our set motors. Set motor 2, that was my motor value, that's where it was plugged into on my Cortex. It was in motor port 2, and this one was in motor port 3. So it has this integer. Why does it have that integer abbreviation there? That's because it's set to float in variables. It doesn't matter if it's integer or float, like I said earlier in the variables, but if you do have it as float, set this, you need to type this integer in front of it. If we open this up, see it says user value down here. You need to make sure to type that int in parentheses in front of it. But if we look at this one below, it's set motor 3, so that's the left side, that's the right side. So this left side, it's negative. It has a negative in front of it. That's because if we look at the little diagram they give for us, counterclockwise is positive, clockwise is negative. The way that this one was put on my robot, or on my lift I mean, it was opposite the other one, so I had to make it negative so it could spin the correct way, because otherwise you can definitely grind some gears, but you might have to mess around with it, but just make sure that you're very cautious, because you can definitely mess up your lift doing that. Now, joystick calculations. Get joystick digital 181. So if that button, which I've put a comment right here, joystick 1, so that's your main joystick, channel 8, that is the section of buttons on the right side of the controller. So 4 buttons in a diamond shape. D button. D button is the lowest button. So if that button is pressed, then the PID requested value is equal to 1364. And if you just press this button, it'll set those values equal to it, and it will automatically go up to that value. And it will stay at that value. So you just have to press it, and it'll go to it. So this is the lowest value, so if I press the D button, it goes all the way down to its lowest point. But what's strange is these values are different. Why are they so different? So when you're calibrating your potentiometers, especially with the high resolution, there is bound to be a difference between the potentiometers. What you want to do is calibrate them at their highest point, because that's where you do not want any difference between the sides of your lift. You need to know 100% that there is no difference between the sides of your lift when it is all the way up at its maximum height. Because if it is twisting while it's up there, it could flip over to the side or something. Or you could grind some gears, or who knows what else. So you want to calibrate it at the very top. If we look, scroll down a little bit, this is my highest value, so 3048, 3048. It's the same on both sides. But there starts to become some difference as it goes lower. This is the middle height, and then even lower, this is the bottom height. So there will be a difference at the bottom, but that's not as big of a deal. And even here, it's only a difference of 100 out of 4,000. Still not much of a difference at all. So this is okay, but you need to use the calibration program to record the values for your robot. So once you have your potentiometers on and they're set, and you have them loosely screwed on to your lift, you need to slowly spin them and calibrate them as you see the printer screen. And you will do that at the maximum height. So you'll do the calibration while it's all the way up, and then record the values as it comes down. So at the middle height, I recorded these two values separately and these two values separately, but these were the same. So these are different, but they're at the same height. The potentiometer value is the only thing that's different, and that is bound to be there. There's no way to prevent it. So that is very essential to keep your lift flat and stable, is recording different values for each side. Just got to make sure that top is the same. Top is the most important. So if I press the D button, it goes down to the lowest value. If I press the L button, it goes to the middle value. If I press the U button, it goes to the highest value. And then this. And this is what I was talking about, the requested value from the main page. We go right here. These two right here, this is where they are used. PID requested value R, I'm reading from right here, equals PID requested value R plus get joystick analog 1, 2 divided by 5. So what is get joystick analog? Because it's up here too in the if. Get joystick analog 1, 2 greater than 10. So if it is greater than 10, or, that's what those little lines mean, or get joystick analog 1, 2 if it is less than negative 10. So if it is greater than 10 or less than negative 10, then start collecting those values, start recording them. So if it is greater than those, it will take those values, or if it is greater than 10 or less than negative 10, it will take those values and it will divide them by 5 and add them to the requested value. But the requested value is what it's setting equal to. So what this causes is it causes it to move in a specific direction. So PID requested value R equals PID requested value R plus the value of the analog as you move it, which is the analog stick, the joystick, divided by 5. So if it's 15, it'll add 15. So that means the lift will slowly start to move up. If you flip the joystick all the way up to, let's say, 100, then it'll add 100, and the lift will start to move even faster up. But luckily we have the drive control limits to stop it from going very fast, which was 100 earlier, so the maximum it can go is 100. So what is this? Why use it? It is joystick control using potentiometers. And there is a joystick control that you can use, but the issue is you cannot put limits on the normal joystick control unless you use a limit switch. So with this, you can set limits on the potentiometer instead of actually having to put limits on your robot. So you have to put limit switches and you have to worry about getting those in the correct position. But instead you can just use potentiometers as limit switches. Now this is completely mandatory. You don't have to have this, but it is what I decided to do, and I wanted to show you that you can do this. You can create the manual joystick using this. And like I said, it can be stopped by limits, which these are the limits, the soft limits down here. Now, as you can see, we have that 3048 again, 3048 again. So we have PID requested value is greater than 3048, or PID requested value R is greater than 3048. Then they're both set equal to 3048. So what that means is they cannot go above 3048. And down here they can't go below these values, which is what the lowest values that we saw earlier were when I pressed the D button, and this one for when I pressed the U button. So that means that they cannot go beyond those. So they're basically like invisible limit switches. And that works very, very well with this joystick control using the potentiometers, because it can't go above or below, so it can't hit points where it can't go to positions where you don't want it to go. I had metal in the way of if it if it would have went below or above that position. So if it would have went above it or below it, it would have hit metal and started stripping gears, which is absolutely what you don't want. And that's what you can use limit switches for. But this is like an invisible limit switch. You don't even have to put it on or program for that or anything. And this is much, much simpler to program than a limit switch. So then we have wait time. Wait time 25. Like I said before in one of my other videos, you don't want this wait time to be any larger than 25, and you can take it out completely. And then lastly, we have our print to screen. Print to screen values, if we look in here, as you can see, we put in a comma, and you can use that comma to separate these. And as you can see, there's a lot. There's the requested value, L, and then there's the PID current value, L, and then the PID drive, L. So it's saying all of those. And then, as you can see, we have %D, %D, %D. You should use these to calibrate it and make sure you know what it's doing. But when you take this to competition and you're trying to compete with it, you want to comment these out. So you can go here and comment out block and comment out block, and all that does is changes them to comments. Now if you don't want them to be comments anymore, you can just go back here and click it and it'll go back to normal. But in your final program, you do not want those there, because they will actually affect how the lift works, just like a larger wait time would. A wait time of 1 second would definitely affect it, and it's the same for the print to screen. So you want to comment those out in your final program. That is the whole program, and I think I am done.